limits at infinity. We are going to continue in this video to find the limit at infinity of functions involving exponential, logarithmic, trigonometric functions, and also determine if a system is in a steady state. Here you see the graph of e to the x, or this is the graph of e to the negative x. This is exponentially increasing function e to the x, and this is exponentially decreasing function e to the negative x. So this also can be, say, graph of 2 to the x, for example. The base is greater than 1, so this is exponentially increasing. Or we may have 1/2 to the x, so this is the graph of exponentially decreasing. So what we see here now, so we're going to use these rules. As x goes to infinity, e to the x. As x goes to infinity, e to the x goes to infinity. So is the case limit x goes to infinity, say 2 to the x. Anything greater than 1 to the power x also goes to infinity. And limit x goes to negative infinity, e to the x goes to, as x goes to negative infinity, e to the x goes to 0. And what about e to the negative x? Limit as x goes to infinity, e to the negative x goes to 0. So this, another way to look at it here, e to the negative is actually same as limit x goes to infinity 1 over e to the x. So you can easily see e to the x goes to infinity as x goes to infinity. So 1 over infinity goes to 0. Also, this is the graph of natural log of x, or in that matter, it is any logarithm of x. So what you see here is as x approaches infinity, limit as x approaches infinity, log of x approaches infinity. Also, we want to talk about tan inverse of x. We want to know about this. Limit x goes to infinity, tan inverse of x, or we call arctan. So this is the graph of tan x. This is the graph of tan x. Y equal to tan x. Now we can see the inverse exists only, it is 1 to 1 only from negative 5 over 2 to 5 over 2. So tan inverse, the x-axis become y-axis, y-axis become x-axis. So you can see the tan inverse graph is like this. It has asymptote at 5 over 2, is a horizontal asymptote at 5 over 2 and negative 5 over 2. So that means as x approaches infinity, tan inverse x goes to 5 over 2, and as limit x approaches negative infinity, tan inverse x approaches, as x approaches negative infinity, tan inverse x approaches negative 5 over 2. Now in this example, let's try to find limit x approaches infinity, tan inverse x over x squared plus 1. So using limit rule, this is the limit of the numerator, limit as x approaches infinity, tan inverse x over limit x approaches infinity, x squared plus 1. So we know as x approaches infinity, tan inverse x approaches 5 over 2. And as x approaches infinity, the denominator x squared plus 1 approaches infinity. So the denominator approaches infinity, the numerator approaches 5 over 2. 5 over 2 is a small number like 1.5 something. And so this approaches 0. Now let's look at this problem. As x approaches 0 plus e to the 1 over x. And also we need to find as x approaches 0 minus e to the 1 over x. Now we know as x approaches 0, 1 over x does not exist. If you can see, this is the graph of 1 over x. That's a reason for this question. So, but if x approaches 0 plus, after 0, say 0 plus, 1 over x approaches infinity. That means as x approaches 0 plus, e to the, this part approaches infinity, right? So that means e to the infinity, so you get infinity over here. because 1 over x approaches infinity when x approaches 0 plus, so e to the infinity, so e to the infinity is infinity. Now what about as x goes 0 negative, limit x goes to 0 negative, 1 over x approaches negative infinity. So as x approaches 0 negative, this goes to negative infinity. So that means e to the negative infinity. So that is mean e to the 1 over x approaches 0. What about this example? Suppose we want to find limit as x goes to infinity of the sine x. Now we know the graph of sine x, the periodic function. So it's going to be like this, right? So as x approaches infinity, so it goes like this. So it's never settling down, mean the limit does not exist. Limit does not exist. As x approaches this go from negative 1 to 1, negative 1 to 1. So this is same thing as in this one again. If you want to find as x approaches negative infinity of sine x, it's also same. It doesn't approach any particular number, so it does not exist. Now what about this one? As x approaches infinity of g of x. Now the sine x behave like this. However, the denominator x, as x approaches infinity, that approaches infinity. So in the numerator you have a number between negative 1 to 1. The denominator you have a very big number. The overall it will result a 0 or some number divided by a big number going to be 0. So this is going to approach 0 in the both way. X goes to infinity or x goes to negative infinity. Either way it goes to 0. Now let's look at this function. This is a combination of exponential versus polynomial. Now if I want to find the limit x approaches infinity of f of x. Now what we see here, the numerator we have an exponent and the denominator we have a polynomial. Now you can remember e to the x is a graph like this. This is exponentially increasing graph. And x to the 9 also is similar to x to the third, and its graph looks like this. Like this. Let's go like that. Now, as you see here, as x approaches infinity, both of them goes to infinity. However, e to the x go much faster to infinity than the any polynomial function. This doesn't have to be x to the 9. Even x to the 99, still e to the x go faster than that one as x approaches infinity. The result in a infinity, because numerator go to infinity faster than the denominator. But now for this one, if you find the limit as x approaches infinity of g of x, now the numerator is a polynomial and denominator is a exponent. So the bottom goes faster to infinity than the top part, the numerator, result in a 0. Over here, however, you have to remember that the coefficient over here is very important on this part. If this is the positive coefficient, so we get a positive infinity. But if you had a negative coefficient here, so this will result a negative infinity. And in this example, we have a logarithmic versus polynomial. Now, if you can remember the logarithmic functions, the graph of log is like this, right? So as x approaches infinity, logarithm approaches infinity, but it approaches infinity much slower than any power functions. Now we have x to the 8, so x to the 8 is graph like this. So it go and x to the minus 1, it just shift down by 1, and still it goes to infinity like that. So what we see here is the bottom or the denominator goes to infinity faster than the numerator, result in a, so if you want to find this, so limit x goes to infinity, f of x will result is 0. And over here, limit x goes to infinity g of x. Now the numerator goes faster than the denominator, results in a infinity. So the constant over here again is important for the sign. Since this is positive, so x to the 8 goes to infinity, so therefore it is going to infinity. Example number 6. A population of colony of bees can be modeled by this formula. And the question is, does a steady state exist? Now, steady state means does it reach a particular number as time goes on? So that means we need to find the limit of this as t goes to infinity. Limit t goes to infinity of p of t. Now, what you see here in this formula, except this is the only part that varies when t varies. Everything else is a constant. And this is the exponentially decreasing function. Now you can remember exponentially decreasing curve goes down like this. Now in this one, t is the time, therefore inherently t has to be greater than or equal to 0. So we know when the t equal to 0, e to the 0 equal to 1. With this 3, so we get 3. 3 times 1 is 3. So this part looks like that. As t goes on, this goes to 0. So this part goes to 0. So what we have is 900 over 2. This is the graph of 3e to the power negative 0.5t. So this goes to 0. So we get 900 over 2, or which is equal to 450. So as t goes to infinity, the population of the bees, the colony, reach 450. So there is a steady state. So it reaches steady state. That is a 450.